Okay. Good afternoon. Nice to meet you today. Can you hear me?
Có.
Okay, thank you. So today we start our course named Electronic Properties Materials. Yes, okay. So concerning this course, you will consider the following chapter. The first one is basic quantum mechanics. The second one is bonding and structure of molecules. The third one, we consider the so-called modern theory of solids. In this chapter, we consider the formation of the band energy band structure for solids, and based on this, we consider the electrical properties solids such as metals, semiconductor, etc. Okay, and the next there will be a semiconductor. Yeah, you know, semiconductor is one of the very important material which can be used for the fabrication of some devices, such as, you know, LED or laser diode, etc. Okay, and the next chapter we consider the magnetic properties and superconductivity materials. And the last one, there must be, optical properties. Yes. And the first 5 chapters will be introduced by me. Okay. And the last one, Dr. Triển will introduce you on materials concerning optical properties. Okay. Okay. So for studying this course, you know, some textbooks can be used. The first one, I would say, there is the principles of electronic materials and devices. The second one is bonding and structure of molecules and solids. Okay, and I would say that we study this, course basically by using the first books, principles, electronics, materials, and devices. Okay, okay. So today we consider the first chapter concerning basic quantum mechanics. Okay. So the object of our study is related to the micro system. Yes, and for this system, normally, the dimension of the particle must be less than 10 minus 9 meter. Yeah. So that means in our course, yes, we consider the behavior of the materials in terms of the behavior of particles like electrons, atoms. Yes, yeah. So you know that all properties depend on the behavior of the so-called valence electron. Yes. Okay. So you know that normally from the point of view of the classical physics, yes, yeah, you know that the motion of the matter normally is considered based on Newton's law, yes, but for our study, for the microsystem, yes, so due to the fact that there exists the so-called wave particle duality. Yes. So in this case, you know that the behavior of the microparticle, yes, must be considered based on the quantum mechanics, yes, and normally for finding wave function as well as the energy of the particle, we should use this Schrodinger equation. Yes, you consider this equation in this part. You know that this equation can be seen as a very basic, equation for the quantum mechanics. Okay, so at first we consider the wave particle duality. Yes, duality. Okay, so you know that until the end of 19th century, yes, from the point of view of the classical physics, so the universe can be seen as matter and radiation. They are separate I mean, in the consideration. Yes, yeah. So constantly matter, you know that there exist particles. Yeah, and these particles can be characterized by the energy as well as momentum. Okay. Yeah. Yeah. And for this, normally Newton law can be used for the consideration of the motion. Yes. Yeah. So how about radiation? Yes. Radiation here, you know that can be seen as electromagnetic radiation, which is a wave, yes, which have the form of waves. Yeah. And radiation can be characterized by the angular frequency denoted as omega, and by wave vector, vector k, yes. And you know that the value of the wave vector is called as wave number, okay? Yeah, and normally wave number k, yes, is equal to the 2 pi per lambda. Yes, 2 pi per lambda. Lambda here is wavelength, yes, of the radiation. I mean electromagnetic radiation. Yeah, and the radio, I mean the electromagnetic wave can be, I mean, characterized based on the use of Maxwell electromagnetic theory. Yes. So from these two separate parts, yes, there must be the combination. I mean, in this case, we have the so-called Lorentz law. Yes, yeah. Based on this, you can see that there is a so-called combination of the, I mean, particle and wave nature of the universe. Okay, and you know that this the point of view of the classical physics, yes, but for the so-called quantum mechanics, you know that the light should have, I mean, wave particle duality, as well as, you know, particle such as electrons, yeah, should have, I mean, or should exhibit the wave particle duality. Okay, so in this part we consider in more detail about this, I mean, duality phenomenon for the light as well for the particle, I mean electron. Okay, so uh, uh, at first we consider a wave particle duality of light. Yeah. So you know that light can be seen as an electromagnetic wave. Yes. Yeah. You know that some phenomena such as interference, diffraction, refraction, etc. Yes, can be explained by the use of theory of waves. Yes, yeah. So please, looking at this diagram, yes, which show the so-called electromagnetic wave. Yes, you know that an electromagnetic wave can be seen as a traveling wave with the time varying electric and magnetic fields. Yes, and you know that the component, I mean, electric field component denoted as EY, and the magnetic component denoted as BZ. Yes, they are perpendicular to each other. Yes, and they are perpendicular to the direction of the propagation of the wave. Yes, yeah, you know this very familiar schematic diagram. Yes, okay, for the electromagnetic wave. Yes, and the electric field denoted as EY at position X at time t. Yes, can be described by the following expression. You know, EY as a function of the position X and time t. Yes, is equal to the E0 multiplied by sine kx minus omega t. Yes, yeah. So you know that this expression for the, I mean, the electromagnetic wave can be derived based on the Maxwell equation system. Yes. So so you know that for this expression, k here, as I told you, yes, is wave number. Yes, k can be determined as 2 pi per lambda. Yes, that means k inversely proportional to the wavelength lambda here. Yes, okay. Omega here is angular frequency. It must be 2 pi f. Yes, f is the frequency. And you know that the velocity of the wave denoted here as a c, yes, is equal to the ratio of the angular frequency omega to wave number k, or is equal to the reduction, yes, of the frequency f and wavelength lambda. Okay, yeah. How about the intensity of the wave? Yeah, you know that intensity of the wave, yes, is proportional to the wave amplitude E0 here, yes, square. Yes, you know. Here, epsilon 0 here is the so-called the absolute permittivity, yes, or you know that it can be seen as a dielectric constant in the vacuum, yes, epsilon 0, yes, okay, yeah. So the wave nature of light, yes, can be used to explain some phenomena such as interference as well as diffraction. Yes, yeah. And here we consider some experiments concerning these phenomena. Okay. So at first, we consider the Young's double slit experiment. Yes, very familiar with you. Yes. Okay. So looking at the schematic illustration of the Young's double slit experiment show in this slide. Here, you know that we have the monochromatic light source. Yes, and the light passing through the two slits. I mean, S1 and S2. Yes, yeah. So due to the interference of the secondary waves from these two slits, yes, in the photographic film, you can realize the dark, yes, and the bright fringes pattern, yes, normally called Young's fringes, yes, yeah. So this fringes pattern are related to the phenomenon of the interference. Yes, yeah. So for the bright fringes pattern, we have the constructive interference. Yes. So in this case, you know that these two rays, yes, I mean one from slip S1 and another from S2, yeah, to the point P in the photographic film, yes, must serve, I mean, identical phase, or they are in phase, yes. That means the path difference between these two rays must be an integer multiples of the wavelength lambda. Okay, yeah, as shown in this expression. Yes, yeah. So n here is integer number. Okay, okay. So for the case of, I mean, destructive interference, yes, yeah, these two waves must be out of phase by the path difference of lambda per second, yes, yeah. So this experiment show that the line should serve, I mean, wave nature. This results into the interference phenomena. Okay. Okay. So the next experiment I would like to show you, I mean, X-ray diffraction. Yes. Yeah. You know that based on X-ray diffraction, we developed the method or the study of the structure, the material, crystalline or polycrystalline, etc. Yes, yeah. So when X-ray are passing, yes, through the single crystal, yes, yeah. So in the photographic film, we can observe some, I mean, bright spots as shown in this picture. Okay, yeah. So in case I mean we have so-called a polycrystalline material. Yes. So X-ray passing through this material, I mean polycrystal. Yes. So in the photographic film, we can observe some bright rings here. Yes. Yeah. And this bright spot as well as a bright ring, yes, can be, I mean, obtained based on the so-called diffraction of the X-ray. Yeah. So that means the bright spot as well as a bright signal can be seen as diffraction patterns. Yes, which have been obtained based on the passing of the X-ray through the material. Yes, yeah. So please look at this, I mean, diagram showing the X-ray diffraction. Yes, yeah, which involves the contractive interference of the wave, which reflected by various, I mean, crystalline plane. Yes, yeah. You can see that these two X-ray should, I mean, as different about 2D time signed theta. Yes, theta here is so-called reflected angle. Yes, yeah, yeah. That means due to the diffraction, so we can get the so-called conjunctive interference of these two rays. Yes, yeah, and the condition for this normally is named as a Bragg diffraction. Bragg diffraction. Yes, yeah. So the expression for the Bragg diffraction condition, yes, can be seen here as 2D multiplied by sine of theta is equal to the integer multiple of the wavelength lambda. Yes, and here is integer to value 1, 2, 3, etc. Okay, okay. So this diffraction of X-ray show, of course, the wave-like nature of the, I mean, X-ray. Yes, this great. Okay, okay. So here I would like to tell you that due to Bragg diffraction, yes, so there must be, I mean, band gap in the energy band structure for material. Yes, we consider this later in chapter 3. Yes, okay, okay. But you know that due to this diffraction, I mean back, so there exists energy so-called forbidden for electron in the material. Okay, okay. So now we consider the particle-like properties of light. Okay, okay. So there are some phenomenon showing or related to this, I mean, particle-like property of light. Yes, the first one we consider the black body radiation. Yes, black body radiation. Yeah. So I think that you know this. I mean, black body radiation. Yeah. So you know that when the matter is heated, yes, it emits thermal radiation. Yes. Yeah. And what is black body? Yeah. So please look at this. I mean, picture. Yes, you can see that a black body can be seen as a cavity. Yes, small one. Yes, in the material that only emit thermal radiation. Yeah, and you know that all incoming radiation must be absorbed totally inside the cavity of a black body. Yes, yeah. So, concerning the black body radiation, there exists classical theory. Yes, Rayleigh-Jeans law. Yes. So, following this law, you know that the spectrum, radiance, yes, as a function of the wavelength lambda. So in this case, you know that the dot line, yes, showing this, I mean, the dependence of the spectrum radiation, yes, on the lambda. And following this law, I mean, Rayleigh-Jean law, you can realize that at the very short wavelength, yes, this parameter must be, I mean, infinite, yes, infinite, yes, okay. And I think that this is not quite good for the physics, yes. Okay, so for the explanation of the dependence of, I mean, spectrum radiation as a function of the wavelength, yes. So Max Planck, yes, already suggested the following. So according to his opinion, the radiation within the black body involves the emission and absorption of quanta of light energy, which is called as a photon. Yes, yeah. So that means the energy of the thermal radiation must be quantized. Yes, and this is related to the oscillation of the molecule in the black body material. Yes. So how about the photon energy? Yeah, the photon energy denoted as the E. Yes, must be the product of the H and new. Yes, new here, and new here is frequency. Yes, yeah. So H here is done constant, or is equal to the H bar. Yes, time by angular frequency omega. Yes, so we have so-called Planck's radiation law as shown in this expression. You know, I lambda here, yes, as a function of the wavelength, as a lambda pi, yes, as well as so-called exponential of the Hc over lambda kt. Yes, T here is the temperature of the black body. Yes, and lambda here is the wavelength of the radiation. I mean, thermal radiation. So in this case, the curve showing the spectrum radiance as a function of lambda can be show or can be presented as in this form. Yeah. So that means you know that there must be a maximum of this parameter. Yeah, and the spectrum radiance must be must reach zero. Yes, at the very long wavelength or at very short wavelength. Yes, yeah. So the higher temperature, yes, the higher value of the spectrum radiance as shown in this diagram. Okay. So if we integrate I lambda over all wavelengths, we can get the so-called Stephan's blackbody radiation law, and so in this expression, yes, P S here, yes, is the total radiative power emitted by blackbody per unit surface area, yes, at temperature T, yes. This, I mean, PS must be sigma S multiplied by T 4, yes. You know this, I mean, radiation law, I mean, black body, okay. Sigma S here is Stephan's constant, okay. So by this, I mean black body radiation, you can come to the conclusion that the electromagnetic wave I mean particle-like behavior. Yes. Okay. So now you consider the next I mean phenomenon related to photoelectric effect. Photoelectric effect. Yes. Okay. So you know this phenomenon. Yes, very familiar with you. Yes, I would like briefly introduce again about this effect. I mean, photoelectric effect. Yeah. So you know that when the cathode, yes, is illuminated with light, yes, which have Okay, sorry. So let's continue. Okay, so if the frequency of the light, yes, must be larger than the critical value, I mean, near zero. So in this case, ammeter should register a current passing through this system. Yes, and you know that the photoelectric current depend on the voltage. Yeah, as shown in this figure. Yes, you know that a photoelectric current increases with the applied voltage and reach saturation value. Yeah, so here showing this curve for different intensity of the light. Okay, and how about the nature of this photoelectric effect? So Einstein, yes, who already developed theory for this effect. So according to Einstein, yes, the light should consist energy package, which is called as a photon. Yes, yeah. So that means the light should consist of, particles named photon here, yes, and the energy of the photon, yes, depends on the frequency nu, yes, as shown in this expression. So when one photon, yes, strikes an electron, so the energy of the photon must be transferred to the electron. Yes. So in this case, electron should have enough energy so that they can move out from the material. Yes. Yeah. So looking at this diagram, you can see the the distribution of the potential energy, yes, in the metal crystal, yes, yeah. So here you know that the potential energy of the electron, yes, inside the metal normally should have the value less than the so-called work function denoted here as I. Yes, yeah. That means electrons become free only when they have enough energy to overcome this. The high potential energy, as well as they should have, kinetic energy. Yes, so that they can move out into the outside of the metal. Yes, yeah. So due to the conservation of the energy, so you know that for the photoelectric effect, yes. So the photon energy, yes, must be the sum of the work function I, yes, and the kinetic energy of the photon, yes, V here is the velocity of the electron, yes. So here you can see that frequency, special frequency, new zero here can be find out based on the equation phi. Work function must be equal to the photon energy h nu zero. Yes, that means you know that the electron emission can occur only when the photon energy, yes, observed by electron must be larger than the work function phi. Yes, okay, okay. So this phenomenon again show the particle-like behavior of light. Okay. So the next phenomenon concerning Compton effect. Compton effect. Yeah. So this effect, you know that when X-ray enter the matter, for example, matter, yes. So it can interact with one of the electron, yes. So in this case, you know that looking at this plot, you can see that the X-ray is deflected, yes, yeah, following this direction. And how about electron? Electron in the beginning considered as in the rest, yes, and after the interaction with the incident X-ray, yes, beam, so electron is recoiling, yes. So you know that the direction of the electron motion, yes, to the angle phi, and it's shown in this diagram, yes. Okay, so yeah, important here that you know that frequency or wavelength of the deflected the X-ray must be changed, yes, or the frequency of the reflected X-ray must be less than that for the incident one, yes, or the wavelength of the reflected X-ray must be longer, yeah, than that for incident one, yes, yeah. So the kinetic energy of the coiling electron, yes, must be the difference between the energy of the incident X-ray, yeah, yeah, photon, and the so-called reflected one here, yes. Okay, so here for the explanation of this effect, Compton, yes. So due to the law of the conservation of the momentum, so you should take into account that X-ray should take, particle-like behavior here. So that because X-ray should take, momentum, and normally momentum is related to the particle behavior. Yes, yeah. So you know that the energy of the particle can be determined based on this expression. Yes. So E here is energy of the particle must be the square root of so the sum of the rest mass square time velocity of 4, yes, and momentum p square time velocity square, yes, yeah. So for the photon, yes, you know, the rest mass must be 0. So in this case, the energy for the photon must be the product of the momentum p and the velocity c. Yes, yeah. So from this, we can determine the momentum p as a ratio to the Planck constant h to the wavelength lambda. Yes, yeah. So by the mathematic treatment, you can get the expression showing the change of the wavelength due to Compton effect. Yes, yeah, as shown in this expression. Okay, okay. So lambda prime, you know, show the wavelength of the X-ray photon after scattering by electron. Yes, okay. So this Compton effect again would show the particle-like nature of the X-ray, yes, of the electromagnetic radiation. Okay, okay. So, how about the duality? Wave particle duality of electron. Yeah, we just consider the duality. Wave particle duality of light. Yes, and now we consider the wave particle duality of electron. Yes, and here we consider the Broglie waves. Yes, yeah. So you know that in the Broglie thesis in 1923, yes, Prince Louis Victor de Broglie already suggested that mass particles, yes, should have wave property similar to electromagnetic radiation. Yes, yeah. So the energy of the particle in this case can be written as the following. Yes, h time nu. Yes, must be the product of the momentum p and velocity c, or is equal to the p time lambda time nu. Yes, yeah. So based on this, we can get the relationship between wavelength lambda and momentum p. Lambda here is equal to h over p. Yes, p here. Yes, yeah. So you know that lambda is wavelength. It shows the wave nature. Yes, of electron. And p here imply the particle nature, of course, for the particle here, I mean, electron here. So lambda here called as de Broglie wavelength. Yes. Okay. Okay. So there are some experiments showing the wave-like nature of the particle, in our case, electron. Yes. So, like for the, I mean, electromagnetic waves, yes, we consider the interference of electron beam at first. Yeah. So here you can see the diagram showing the experiment for the interference of electron beam. Yes. So electron can be emitted from the hot filament. Yes. And electron can be accelerated by the application of an external voltage, in this case of 50 kilovolt. Yes. So in this experiment, yes, how about the energy of electron? Yes. You know? Mm-hmm. Yeah. The electron energy must be 50 kilo electron volt. Yes, kilo electron volt. So simply, yes, you can say yes. So electron beam, yes, passing through the double slit here. Normally we call young slits here. Yes. So in the fluorescent screen, yes, we can observe, I mean, some bright pattern and dark pattern as shown in this screen. Yeah, and this pattern here you can see here as can be considered as electron diffraction fringes. Yes, yeah, and this is related to the interference. Yes, the electron beam. So in this case, electron behave as a wave. Yes, yeah. So you know that there must be, I mean, wave particle behavior in some time. Yes. Mm-hmm. Yeah. So the next phenomenon showing the, I mean, wave-like nature of electron. Yes. Yeah. Which is electron diffraction. Yes, electron diffraction. So please look at this diagram. So when an electron beam, yes, passing through the aluminum sheet, yes. So in this case, we can obtain, I mean, bright ring pattern. Yeah, yeah. And this bright ring pattern is related to the diffraction pattern, yes, due to interference of the reflected beams. So we can get, I mean, bright ring here, which related to the, I mean, diffraction phenomenon. Yeah. So in this case, you know that electron should serve, I mean, wave-like nature. Yes. And here, very interesting that if we bring a magnet to the screen. Yes. So you know that the diffraction pattern become distorted. Yes, as shown in this picture. Yeah. So it occurs due to the influence of the magnetic field to the moving particle here, electron. Yes, and you know that this you know that the X-ray diffraction, yes, pattern would not be affected by magnetic field yet. But here, you know that electron diffraction pattern can be affected by magnetic field is due to the fact that electron beam and the charge carrier flow. Yes, yeah. That's why so that electron can be affected by the magnetic field. Okay. Okay. So based on the electron diffraction, yes, we can develop special method for the investigation of the structure materials. Okay. Okay. So we just consider the wave particle duality of light as well as electron. Yes. Yeah. So very important here. You come to the conclusion that the microparticle like electron, yes, should have wave particle duality. Yes, yeah, they should have both wave as well as the particle nature or behavior. Yes, so very important. I would like to say that one question raised that when the wave behavior or when particle behavior the particle can be realized. Yes, yeah. So I would say that this behavior wave particle like behavior can be realized only when the particle interacts with the matter. Yeah, you can see here. Okay. In some case, the particle can behave as wave nature. Yes, wave nature. Yes, like for the electron diffraction, as I told you just before. Okay. Yeah. So due to the wave nature, so the behavior of the microparticle can be very specific. Yes. Yeah. So one of the phenomenon related to the uncertainty, yes, uncertainty of some physical parameter, yes. And now we consider the Heisenberg uncertainty principle. Okay. Okay. So at first, we consider the Heisenberg uncertainty principle for position and momentum. Yes. Okay. So for the position, delta is termed as uncertainty of the position. Yes, and delta p h, yes, here, yes, is denoted as uncertainty for the, momentum component ph here. Yes, yeah. So if delta x and delta px, yes, are the respective uncertainties in the simultaneous measurement of the position and momentum of particles along a particular coordinate, in our case, x here, yes. So the Heisenberg uncertainty principle can be stated as the following, yes. Delta x here, yes, multiplied by delta px here must be larger than h bar. Yes, yeah, here. H bar here, you know that must be 2 pi per, h must be h per 2 pi. Yes. Mm-hmm. Yeah. Okay. So this, Heisenberg uncertainty expression of the, position and momentum along the x coordinate. The same expression for the other coordinate, y and z. Yes, yeah. So looking at this, expression for the Heisenberg uncertainty. Yes. So we can realize that due to the wave nature of quantum mechanics, yes, we cannot exactly and simultaneously determine both the position and momentum of particle along a given coordinate. Yeah, so it's very, very interesting. Yes, so it means if we would like to determine exact value of the position, that means delta x must be very small. Yes, but you know that delta px, yeah, at least must be h bar over delta x. Delta x here, yeah. That means delta x, yes, smaller. So delta, how about the value of delta px? Yeah, delta px must be larger. Yeah, so that means we cannot exactly, and very important here, simultaneously, yes, know or determine both the position and momentum, yes, of particle along the given coordinate. Okay, okay, it's quite different for the classical, mechanics, yes, classical mechanics. So in in this case, you know that delta h and delta ph can be 0. Or in this case, delta x or delta px here, they can be 0, or each of them can be 0. Yeah. So for the so-called classical theory, so we can determine exactly and simultaneously both position and momentum, but quite different for the microparticle system. Yes, yeah. So please remember it. Okay. So we have another equation for the Heisenberg uncertainty principle. For the energy and time. Yes, yeah. So the relationship between the uncertainty in the energy denoted as the delta E, yeah, of a particle, and the time duration delta T, yes, during which the particle possesses the energy, or during this time the energy of particle is measured. Okay, so the uncertainty relation for the particle energy and time can be written as the following. Delta E, yes, here uncertainty of energy, yes, multiply by delta T, consider as the uncertainty of time, yes, must be larger than h bar. Yeah, it's equal to pi. Yes, yeah. So in this case, you know that based on this expression for the uncertainty related to energy and time. Yes, you know that we cannot exactly and simultaneously determine or know both the energy and time particle. Yeah, so it means that it, the particle have the, certain value of the energy. Yes, yeah. So in this case, you know that the uncertainty of time must be very, very large. Yes, or if we know the exact value of the lifetime of the particle. Yes, so in this case, you know that the energy of the particle must not be unique. Yeah, or in this case, the energy level of the particle can be expanded. Yes, yeah. So it's very important when we consider the, behavior of the electron, yeah, when they are excited into the high energy level. Yes, and maybe we consider this in the chapter related to the optical property, mainly exactly for the lasing phenomenon, the solids. Okay, okay. So how about the relationship? Yes, between the classical physics, between classical, mechanics, yes, and the so-called quantum mechanics. Yeah. So please imagine that if h bar equal to 0, yeah, what happened in this case? So in this case, you know that delta E multiplied by delta T, yes, must be 0. So in this case, you know that delta E can be 0, or delta T can be 0 simultaneously, yes. Sorry. So in this case, you know that if h bar is equal to 0, so we can deal with the classical mechanics. Yeah. So I would say that classical mechanics can be the case for the quantum mechanics. Okay. Yeah. So it's very, very interesting here. So we just consider the Heisenberg uncertainty principle, yes, for energy and time, as well for the position and momentum, yes, yeah. And I would say that this uncertainty occurs due to the wave nature of the particle, yes. Okay, so here I would like to show you an example for the uncertainty principle on the atomic scale. Yes, yeah. So here, if we consider an electron which confined in the region of not 0.1 nanometer, yes, and this sign can be seen as the typical dimension of atom. Okay, so what will be the uncertainty in its momentum and as well as in its kinetic energy? Yeah. So here we use the Heisenberg uncertainty relationship. Delta H multiplied by delta pH must be H bar. Yes, yeah. The lowest value of production. Yes. Yeah. So in this case, we can determine the the value of the uncertainty of momentum delta pH. Yeah, this should be about 10 to minus 24, yes, kilogram meter per second. Yeah, and from this you can find out that the uncertainty of the velocity, yes, delta v must be about 10⁶ meter per second. So a very large value. Yes. Yeah. And how about the value of the kinetic energy? Yeah, by calculating, yes, we can get so-called the value of 3.82 electron volt. Yes. Yeah. 3.82 electron volt. Yes. Yeah. So you know that how about the thermal energy of at the temperature, I mean room temperature. Yes, yeah. This must be 0.026. Yeah, 26 times 10 to minus 2. Yes, electron volt. So that means the kinetic value here is very large. Yes, very large. Okay. So we just consider some issue concerning, I mean, Heisenberg uncertainty. Yes, yeah. And now we shift to the next issue. Yes, concerning the Schrodinger wave equation. Yeah. So I would say that this wave equation can be seen as a very important basic equation, yes, for the quantum mechanics. Yes. So based on this equation, you can find out the wave function and the energy of the particle. Yes, as well as you know that the probability of finding electron somewhere in the space. Yes. Okay. So at first we consider the wave function. Yes. Yeah. So you know that in 1926, yes, scientist Max Born already suggested wave interpretation for the wave-like behavior of electron. Yeah, and this wave can be seen as a plane traveling wave, and can be described by the wave function for the electric field as shown in this expression. Yes. So electric field E as a function of the position x and time t here must be equal to the electric field amplitude T0, yes, multiplied by sine of kx minus omega t. Yes, yeah. So generally, wave function for the electron can be represented by the function psi. The function psi, the wave function, yes, psi here can be seen as a function of the position, depend on the x, y, z, and also this function depends on time here. Yes, and very important that if we know the wave function, yes, we can determine the probability of finding the electron per unit volume, yes, at position x, y, z in space, and at the given time t. Yeah, so you can see that this, I mean, probability density, yes, can be determined as the absolute value of the wave function psi square, yes, and it is equal to the product of the complex conjugated wave function psi star here, yes, time wave function psi here, yes, okay. So if we know the probability density of finding electron, yes, per unit volume, and at a given time t, we can determine the probability of finding the electron in a small elemental volume dV. Yeah, yes, at the position x, y, z, and at time t. It can be as absolute value of the wave function psi square time the elemental volume dV. dV can be seen here as a dx and dy and dz. Yes. So for the one dimension, I mean along the in our case x coordinate, yes. So a wave function can be seen as a function of x and time t here. Yes. So in this case, absolute value, absolute, I mean value of wave function psi square. Yes. Time this must be the probability of finding the electron between x and x plus dx, yes, at the time t. Yeah. Okay. So if we know the wave function, yes, we can find out the total probability of finding the electron in so-called all space. Yeah, and this I mean total probability value must be unity. Yes, yeah, and so this I mean integration. Yes, finding total probability. Yes, okay. And later we know that we can use this expression so for the some configuration concerning wave function. Yes, okay. So how about the property of valid wave function? Yes, yeah, okay. So we consider this, I mean, later after short break in 10 minutes. Okay, so thank you. We have short break now. Okay, so let's continue our lecture today. So we just consider the wave function for electron, yes? And now we consider properties of valid wave functions, yes? So how about the condition on the wave function? Yeah. So the first one, you know that the wave function, yes, must be finite everywhere. Yes, finite everywhere in the space. Yes. Why? So in this case, you know that we can avoid the infinite probability of finding electron. Yes. Everywhere. Yes. In the consider region. Okay. So the second condition states as the wave function, yes, must be single value. Why? Yeah, it's because that the value of the probability of finding electron must be single. Yes, yeah, and the wave function, you know, must be twice differentiable. Yes, this means that wave function and its derivative must be continuous. Yes, must be continuous. Yeah, yeah. This condition, you know that uh, for finding wave function, we should use the Schrodinger wave equation. Yeah, and this equation is a second order. I mean, different equation. Yes. So the last condition states as follow that in order to normalize the wave function, yes, it must approach zero as x approaches infinity, yes, yeah. So it means that for finding, I mean, an exact formed wave function, we should normalize a wave function so that we can find out the needed coefficient. Yeah, we can see this later. Yes. So in this case, you know that all solutions that do not satisfy this property do not generally correspond to physically realizable circumstances. Yes. It means that some solution, yes, related to the wave function as well as corresponding energy, yeah, can be not valid because that is not satisfy the physics parameter which we have to measure or which we have to determine. Yeah. For example, the probability of finding electron, yes, or energy etc. Okay. Okay. So here some plot showing unacceptable form of the wave function psi. Yes. So the first case showing that wave function psi not continuous. Yeah. Okay. And the second plot showing the first derivative of the wave function psi of in accordance to x here, which is not continuous here. So here. Okay. The last plot showing that the wave function psi here not single value here. So, for example, at this position, the wave function should have 3 values here. So, in this case, you know that we cannot accept such a wave function, and because you know that at the position x, yes, as a value of the probability of finding electrons, yes, must be unique, yes, okay, or must be single. Okay. So now we consider the time-dependent Schrodinger wave equation. Yes, yeah. So the time-dependent Schrodinger wave equation, you know, and describe how the wave function of the particle will evolve in time. Yeah, yeah. So the Schrodinger wave equation in its time-dependent form for a particle which have energy E moving in the potential V in one dimension can be given as in the following expression. Yeah, here you know that on the left side there is I multiplied by h bar. Yes, time the partially first derivative of the wave function in accordance to the time t. Yes, yeah. And the right side, you know that consists of 2 terms. The first term is a minus h bar square over 2m. Yes, multiplied by second derivative of the wave function psi in accordance to x. Yes, and the second term is a product of the potential energy V and the wave function psi. Yes, yeah. Here I here is an imaginary unit. Yeah, you know that I square must be -1. Yes, yeah, of course. Yeah. And in our case, we consider the one dimension problem. So here, psi as a wave function depends on x in our case. Yeah. And as I told you that the Schrodinger equation, yeah, the fundamental equation for quantum mechanics. So based on this equation, we can determine the wave function. You know that wave function, yes, can be used to represent the state of the electron. Yes, yeah. So based on this equation, beside wave function psi, we can determine the energy value for to consider a particle. So that's why this equation can be seen as a fundamental equation for quantum mechanics. The role of this equation can be seen as a Newton law for the classical mechanics. Okay. Okay. So now we consider to consider, I mean, the general solution, yes, of this equation in case the I mean potential energy is zero. Yes, that means in this case we consider the equation in Schrödinger, yeah, or the free electron. Yes, yeah. So in this case, the form of the I mean Schrödinger wave equation can be shown be so represented in this I mean expression. So in this case, v is 0. So you know that v times psi must be 0. That's why we have such form of the Schrödinger equation. Yes, yeah. So you know that the wave function particle having a fixed energy E, yes, must represent a wave traveling, yes, in the positive x direction, yeah, which can be shown on the following expression, yes. So you know that wave function psi here, yes, can be seen as a product of the coefficient A, yes, and expression of I multiplied by kx minus omega t. Yeah, yeah. This I mean expression normally represents the so-called plane traveling wave of electron. Of I mean free electron. Yes. Mm-hmm. So or you have that sine can be a times cosine k x minus omega t, yes, plus I sine k x minus omega t. So you know that k here is a wave number, yes, okay. So if we make so-called the first derivative of the wave function psi, yes, in accordance to time t, we can get the result as minus I time omega and time psi here. Yes, yeah. So in this case, you know that the left side of the Schrödinger equation it can be h bar, yes, time omega divided by wave function psi here. Yes. Okay. So how about the right side of this equation? So the second derivative wave function psi in accordance to x, yes, must be minus k square times psi, yes, and you know that the right side of this equation must be h bar square, yes, multiplied by k square over 2m, or this ratio multiplied by wave function psi, yes. Yeah, m here is electron mass. Okay, so from this we can get that h bar omega must be h bar square multiplied by k square over 2m. Yeah, so left side here h bar multiplied by omega must be energy. Yeah, and energy here is so-called here, yes, is the so-called total energy of electron. Yes, yeah, and this energy must be kinetic one. Yeah, and that means the energy of the electron, yes, must be a kinetic energy, which is proportional to the wave number square as shown in this expression. Yes, so please remember the form of the energy of the free electron. Yes, you know that for free electron there exists the so-called kinetic energy. Yes, which depend on, proportional to the wave number square, k square here. Yeah. Yeah. So you know that we can find out energy for free electron based on the Schrodinger wave equation. Okay. Okay. So here I show you again the expression for the wave function for the free electron. Yeah, electron. That means in case the potential energy is 0. Okay, so looking at this, you can see that the wave function, yes, describe the plane wave traveling in the x direction. Yeah, and A here is the amplitude of the wave function. Yes, in general, yeah, this parameter can be complex. Yes, so you know that the wave function generally is a complex function. Yes, yeah, yeah. You know that it's due to the fact that sorry. Okay, let's continue. So you know that wave function can be represented in the complex form. Yes, yeah. It's due to the fact that based on the wave function, yes, we can determine the probability of finding electron. Yes, here you know that this parameter can be the product of the so-called complex conjugate wave function psi star, yes, multiplied by wave function psi. Yeah, okay, and this results into the wind value of the probability density finding electron. Okay, okay. So here I would say that the physical the value which can be measured, yes, must be green, yes, yeah. So that means you know that the probability, the momentum, as well as the energy must be green parameter. Okay, okay. So now we consider the normalization and probability. Yeah. So you know that we can determine the probability density of finding particle or in our case electron. Yes. Yeah. In the one elementary volume, yeah, delta V, yes, at the time t. And if we know the probability density B as a function of H, yes, so we can find out the or we can determine the probability of finding electron or particle being between x and x plus dx, as shown in this expression. Yes. So p as function of x here is so-called probability density of finding electron. Yes. At the position x. Yes. So P multiplied by dx, yes, must be psi star multiplied by psi and times dx, yes. Psi star here, as I told you, that is a complex conjugate wave function, yes. Yeah. So if we try to find out the value of the probability of finding the particle being between being in the range from x1 and x2, so we can we would integrate from x1 to x2 the psi star multiplied by psi and dx here. Yes, yeah. So in case if we would like to normalize the wave function, so in this case, you know that the probability the particle being somewhere on the x coordinate must be unity, or you know that. Oh, sorry. Okay, so that means for the normalization of the wave function, we should take integration from minus infinity to the plus infinity of, psi star times psi dx, and this integration must be unity. Yes, and this expression used for the normalization of the wave function, which can be used in some exercises later. Okay, okay. And now we consider the time independent Schrodinger wave equation. Yeah. So in some case, you know that the potential, yes, will not depend explicitly on time. Yes. So in this case, the wave function dependence on time and position can be separated in the so-called Schrodinger wave equation as the following. Yes. So in this case, wave function psi can be represented as a product of the part of wave function which depends only on the position, denoted here as a psi as a function of x. Yeah, and another part of the wave function which depends only on the time t. Yeah, so if we put this, expression into the Schrodinger wave equation, we can get the following expression. Yes, yeah. So, and then if we divide this, both sides of this equation by the product of psi as function of x and phi as function time t. Yes. So we can get the following expression. Yes. On the left side, we have I times h bar. Yes. Multiplied by 1 per f t. Yeah. And multiplied by first derivative of f in accordance to time t. And how about the right side? You can see the right side consists of, two terms. Yes, here we have minus h bar square over 2m. Yes, multiplied by 1 per psi. Yes, and multiplied by second derivative of wave function. Yes, in accordance to h, and plus v. Yes, potential energy as a function of position h only here. Yeah. So looking at this, function, equation. Sorry, this equation. Yeah, you can realize that the left side depends only on the time t. Yeah, and right side of this equation depends on only position x. Yeah, it results into the fact that each side of this equation must be equal to constant. Yeah. So in this case, we consider the time-dependent side of this equation. I mean, we have I h bar, yes, multiplied by 1 over f, yes, and multiplied by df per dt here, yeah, must be equal to b, yes, to b, b here, yes. So in this case, by integration, both sides of this, I mean, equation, yes, and then we can get so-called expression for the function f as a function which of time t, yes, ft here, yes, is equal to the b bt over I h bar, yes, or equal to the exponential of minus I dt over h bar, yes, yeah. So by solving the left side part, we can get the expression for the f as a so-called part of wave function which depend only on the time. Yes, yeah, and you know that it is proportional to the exponential of minus IBT over h bar here. Yes, okay. So as you know that we have a problem with the three particles. So in this case, you know that the wave function time can be represented as a, yes, coefficient a, yes, multiplied by exponential of I time k x minus omega t. Okay, here k is you know wave number. Yes, yeah. Omega here is angular frequency 2 pi f. Yes, okay. So uh, that means in this case, the part of wave function psi, which depends only on the time, can be as exponential of minus I omega t. Yeah. So from this obtained expression, we can get a b, yes, as a product of h bar and angular frequency. Yeah. So you know that h bar times omega, yeah, must be, I mean, energy, must be energy. Yes. Okay. So that's why here we can come to the conclusion that B represents energy, or B is equal to E. Yes. So in this case, we can rewrite our Schrödinger equation as the following. Yes, minus h bar square over 2m. Yes, multiplied by second derivative of the wave function psi. Yes, in accordance to x plus potential energy V as a function of the position x multiplied by wave function psi must be equal to energy E times wave function of x here. So that means we can get the form of the so-called Schrödinger equation. Yes, it doesn't depend on the time. Yes. Okay. Okay. So here we're very interesting. Yes. Please looking carefully at this equation. Yeah. So here the left side, yes, it can be seen. Normally you can see seen here. Can consist of two terms. Yes, the first term is related to the kinetic energy, and the second one related to the potential energy. Yes, okay, yeah, and E on the right side can be seen as the total energy. Yes, and sometimes this equation can be represented in the so-called operator form. Yes. Okay. So here you know that we just have the time independent Schrödinger wave equation. Yes, and this equation can be represented in the operator. Yeah, and this equation can be given as the following. Yes, h hat here, yeah, h with hat here, yeah, is a Hamiltonian, yes, operator. Time wave function psi must be the total energy of the particle time wave function. Yeah, and the Hamiltonian operator h with hat here, yes, must be minus h bar square, yes, over 2m multiplied by partially the second derivative in accordance to h, yes, plus potential energy V. Yes. So I would say that the Hamiltonian operator can be seen as an energy operator. Yes. Yeah. Yeah. Looking at this, expression, yes, the first term is related to the kinetic energy. Yes. And the second term related to the potential energy. Yes, yeah, yeah. In our case, we consider one dimension. Yes, but for a general case, yes, for 3 dimension, yeah, this second derivative, yes, can be represented as a Laplacian operator. Yeah, this one. Yes. Okay. Okay. So we just consider the so-called time independent, yes, showing the equation time independent, yes. So now we consider, stationary states, yes, yeah. So the wave function, yes, can be written as the following: psi as function of position and time t, yes, must be the product psi as a function of the position multiplied by exponential of minus I omega t. Yeah, that means in this case, that we consider the case when the potential energy is doesn't depend on time. Yes, right. We have to time independent Schrödinger wave equation. Yes, yeah. So in this case, based on this, expression for the wave function, we can determine the probability density finding electron, yes, as shown in this expression. Yes, psi star times psi, yes, must be psi square multiplied by exponential of I omega t time exponential of minus I omega t. Yes, as I told you that psi star is a complex conjugate to psi. Yeah. So this product must be, psi square. Yeah. You know the normal psi here is wave function which depends on only the position x in our case. Yeah. So it means that the probability here must be constant in time. Yes. Yeah. So in this case, we have the standing wave phenomenon. Yeah, and this related to the stationary state for electron. Yeah, yeah. So that means the stationary state for electron, yes, occurs when electron wave show the phenomenon of standing wave. Yeah, yeah. So we consider the next issue concerning electron behavior of electron on the infinite potential well. Okay, yeah, and you know that standing wave, yeah, can be seen as a combination of two waves moving in opposite direction. Yes, and each wave must have the same amplitude and frequency. Yes, you know. Yeah, and this phenomenon, standing wave, is a result of interference. Yeah, that means this occurs when waves are superimposed. Yes, and the energies can be either added together or cancelled out. Okay. Okay. So, yeah. Now we shift to the next issue. Yeah. I mean, we consider the infinite potential well, a confined electron. Yes. Yeah. So this problem very, very interesting. Why? And normally by looking at the, electron which is confined in the infinite potential well. So in particular, we can consider the behavior of electron, yes, in the so-called quantum well. Yes, yeah, yeah. You know that for the, nano dimension of the matter, so we can deal with quantum well, yes, or quantum dot. Yeah, okay. So later someone would like to investigate some, nanomaterial. So I think that this is the knowledge concerning the, the confined electron in the infinite potential well. The good knowledge for you. Yes. Okay. Okay. So if we consider the behavior of the electron, yes, when electron is confined to the certain region between 0 and A, as shown in this schematic diagram. Yes, yeah. So here you can see that electron, yes, we try to find out the behavior of electron, which confined in the region between 0 and A. Yes, or A is so-called the width of the potential well in this case. Yes, and outside of this region, you can see here that the potential energy must be infinite. Yes, yeah, okay, yeah. So you know that in this case, electron cannot escape from this potential well. Yes, okay. So if we know the wave function of electron size, so you know that the probability of finding electron, probability density, yes, of finding electron must be 0 outside of this region, yes, outside of the region between 0 and A, yes, and that means the wave function psi must be 0 when x is less than 0 or larger than A, yes. So based on this condition, we can have so-called second order linear differential equation as shown in this expression. Yes, yeah. So due to the fact that the potential energy must be zero inside the region between 0 and A, so know that we can get this expression for the Schrödinger wave equation. Yes. So second derivative of wave function psi in accordance to H. Yes. Plus 2 me over h bar square multiplied by e and psi must be 0. Yes. In this equation, yes, me here is electron mass. Yes. Okay. Yeah. And this equation, you know, that second order linear differential equation. Okay. Okay. So we continue considering this, I mean, interesting issue later next week. Okay. So let's finish our lecture today. Yes. So I would like to tell you that you should look at the own example, yes, represented in the book. I mean, of CASA. Yes, yeah. I will not give you exercises, but please, so look at the own example. Yes, represented in the textbooks of the CASA. Okay. Okay. So it's time. Yes. Thank you for attention. Okay. Yeah. So, do you have any question?
Em thưa thầy ạ.
Yes.
Thầy có thể up slide lên luôn được không ạ?
Slide tôi đã up lên rồi. Các em kiểm tra lại đi. Tôi hôm qua đã up cho các em cả slide và cả sách rồi nhé. Thì các em lần sau học ấy thì cố gắng mở ra để coi như được sử dụng để cùng nghe cái bài giảng thì nó sẽ rất là có hiệu quả hơn nhé.
Dạ vâng. Thế em lên mạng em tìm sách tiếng Việt đấy ạ, mà lại không có, thầy có không ạ? Thì cho em xin.
Chết rồi. Thế này, tôi cũng xin lỗi này, tức là sách tiếng Việt thì hiện nay là không có, rất tiếc là như thế. Cho nên là ở đây tôi nghĩ là cố gắng nếu như mà các em thấy chỗ nào không hiểu lắm thì có thể là cũng nên hỏi, đặc biệt là có thể một số thuật ngữ đấy, thì có thể là trong cái bài tới, trong những phần tới có những thuật ngữ đặc biệt thì tôi sẽ nói với các em để các em có thể để dễ dàng trong vấn đề cảm nhận tiếp thu bài giảng nhé. Thế còn thì sách tiếng Việt thì tôi nghĩ là nó không có, hiện nay chưa có gọi là gì, tác giả nào đưa ra cả, mà ở đây đúng là cái câu hỏi của em cũng là rất hay, để có thể là chúng tôi cũng sẽ quan tâm trong cái việc mà phải viết giáo trình. Đấy, thì cái này thì tôi cũng sẽ trao đổi với các thầy liên quan để có thể làm sao mà có được cái sách tiếng Việt. Yeah. Rồi, thế thì cảm ơn các em nhé. Thế thì nếu không có vấn đề gì thì ta nghỉ ở đây. Yeah. Rồi.
Thế không có sách tiếng Việt cũng không có slide tiếng Việt luôn hả thầy?
Slide tiếng Việt à? Slide tiếng Việt. Tại vì đây là mình học tiếng Anh mà thì phải theo tiếng Anh chứ, còn sai thì slide tiếng Việt thì gay go quá.
Không, con nhiều cái nó khó hiểu thì đọc sang slide tiếng Việt nó dễ hiểu rồi thầy ạ.
Nhưng mà vì là chương trình chúng ta là chương trình tiên tiến mà, đúng không? Thì cũng muốn là các em học mà bằng tiếng Anh để sau này các em có cơ hội khi mà ra nước ngoài ấy, thì đương nhiên là mình phải bằng tiếng Anh rồi, đúng không? Đấy thì có thể là mình cố gắng đi nhé, thì mình sẽ có được cái kiến thức mà không chỉ là về chuyên môn, mà mình lại có kiến thức cả về các cái vấn đề về ngôn ngữ nhé. Đấy thì tôi nghĩ là nếu mà mình mà học bằng tiếng Anh như thế này ấy, thì sau này cái việc mà mình có thể trình diễn rồi báo cáo hội nghị các thứ thì tôi nghĩ cũng là cái để mà làm quen em ạ nhé. Tôi cố gắng lên trong những cái này thì có thể là trong những cái phần tới thì tôi sẽ có những cái thuật ngữ mà đặc biệt thì tôi sẽ dịch cho tiếng Việt trước để cho các em có thể tường minh hơn nhé.
Thưa thầy, thầy cho em hỏi là môn này có đề cương không ạ?
Đề cương thì thực ra là các cái phần chính thì tôi cũng đã nói, có thể là này, trong cái có thể là gì trong cái chương này tôi sẽ có thể đưa ra những cái phần chi tiết hơn mà liên quan tới cái việc mà ta những mục nhỏ ở trong chương này thôi nhé. Thì đề cương thì nó sẽ liên quan tới cái học phần, đúng không? Đấy. Thì cái này thì các em đọc trong cái quy định học phần thì cũng phải có những cái người ta yêu cầu cái thứ gì đấy nhé. Đấy. Thế thì tôi nghĩ là tất nhiên thì chúng ta học cái này thì sẽ có những cái phần mà sẽ phần chú trọng hơn thì chỗ nào mà chú trọng thì tôi có thể sẽ dừng lại lâu hơn, còn cái chỗ nào mà nó còn những phần khác thì có thể là biết nhanh hơn để đảm bảo cho về cái mặt là gì cái tiến độ của học tập của chúng ta nhé. Rồi. Rồi, nếu các em không có ý kiến gì ta nghỉ ở đây nhé. Có gì thì cần thì chúng
thầy
ta
ơi, thầy cho tí nữa thầy gửi slide lên trên file cho bọn em nhé.
Tôi xin lỗi là cái slide này ấy, tôi đã gửi cho các em rồi. Các em vào trong cái chỗ mà gọi là cái channel của nhóm ấy, thì là trong cái chapter 1 đấy thì là ở đấy tôi đã gửi cái slide rồi, và tôi còn gửi
Dạ,
cả
đây em thấy là nãy em vào nó bị lag, thế là em thấy 0.0, bây giờ em thấy rồi ạ.
đấy, thế rồi cả sách, cả hai cái book đấy là tôi cũng gửi cho các em rồi từ hôm qua mà.
Vâng ạ,
Nhớ cố gắng.
cảm ơn ạ. Vâng ạ.
Rồi nhé, tôi cảm ơn, chào các em.